wait for a while. All right, let's look at mathematical modeling of mechanical systems. So for the mechanical system, we have to consider two what we call it movement of the mechanical system, which is one is the translational, the other one is rotational. Okay. Translational is basically it's very simple. You have a point A and you have a point B. Basically, translational is just a movement or from point A to point B, or you can say this A to A prime. Okay, but for the rotational is actually it rotates across its axis. For example, you have let's say you have X, you have Y, and you have Z here. So rotational is actually the rotational on its axis. You can have a rotational about the X-axis. You can have the rotational about the Y-axis, and you can have the rotational at the Z-axis. Okay. Let's see for the translational first. For the translational, in this course, we will only consider three components that can be used in the translational movement. We have a spring, we have a viscous damper, and we have a mass. Okay, so for the spring, we have the coefficient we define as K. K. Okay, so the force that moves the spring is Ft, and then the translational movement is, we call in this case, is Xt to the right. Okay, Xt to the right, and we can have force displacement for the Ft is equals to Kxt. Kxt. For the impedance, we can have this f over x, fs over xs is equals to k. Okay, for the viscous damper, we have ft equals to dx over t, dxt over dt, dxt over dt, or you can have in this form fv x dot t. And then for the impedance of this viscous damper is actually fvs. Okay, and for the mass is actually we have ma. Remember, f equals to ma. So a in this case is actually 2 times differentiation of the xt. So we have x double dot t. So for the impedance is we have ms square. So you need to memorize, or you need to familiarize yourself with this component in order for us to do the analysis, translational analysis of these mechanical components. All right. So this is the first example here. So we have 3 components. We have K we have spring, we have the viscous damper, and we have the mass. And this is the wall. So this wall is fixed, it's not moving. And then we have the mass M here that is connected to the wall via spring and via the viscous damper. Okay, as I already have mentioned in the previous slides, we have the coefficient for the spring is K, and the coefficient of the viscous damper is Fv. And let's say we have the force to the right. Okay, we have force to the right, Ft, and the movement of the force to the right is Xt. Okay, so to analyze, this is 1 degree of freedom, 1 degree of freedom example, because we only have one mass. If we have two mass, we will have 2 degree of freedom. If we have 3, we have a 3 degree of freedom. Okay. Okay. Let's do this step by step. Okay. For this example, we have to consider the mass m only, because it is only 1 m here. So we only have to consider this m. Okay, this mass m. Okay, when we apply force to the right, okay, when we apply force to the right, force is Ft, we apply to the right, what will happen is that there will be a counter force to the left of the spring, of the viscous damper, and of the mass itself. Because when you move something from the initial condition, there will be initial, right? There will be initial, right? And then when you pull the mass to the right, there will be counteraction to the left. Okay? Counteraction to the left, which is when you see this table, you have the force displacement relationship here. Force displacement relationship for the spring is kxt, and for the viscous damper is Fv x dot t, and for the mass is mx double dot t. Okay, so we use the force displacement relationship in this example here. So we have for the spring we have kxt, for the Fv we have fx dot t, for the m we have m double dot t. Okay, and we can transform this to the Laplace, to the S domain, where we have initial condition equals to 0, where we have the initial condition equals to 0, we only have this term. Kxt become kxs, fv dx dt become fvs xs, and for the m, we have ms square xs. Okay, so refer to this table again, this portion, okay, this portion. So this is the impedance. This one you use in this when you transform from the time domain to the S domain. Okay. All right. So we can put together in one equation. So we have 1 degree of freedom. We only have one equation where the force that apply to the mass is equals to the summation of the counter force due to the spring, due to the viscous damper, and due to the mass itself. So we put in together, and then we transform from the time domain to the S domain. So we have this term. Okay, we have this term, and we can, since it only has one translational move in the x direction, we can lump together this component ms square plus fvs plus k of xs equals to fs. So we can find the transform. We can find the transfer function gs, which is the output is xt, the input is fs, and the output is the movement of the mass, and the input is with force that is applied to the mass. So we have xs over fs. So in this example, it's very simple. You just rearrange this equation to this equation. You will get xs over fs equals to 1 over ms squared plus fvs plus k. Okay, so to sum it up for this example, we can say that we can put in we can come up with an equation of this 1 degree of freedom by this. We have a sum of impedance multiplied by xs equals to sum of applied forces. Okay, so in this case, this is the sum of impedance. This is the sum of applied force. Okay, so this is the sum of applied force. Since it's only 1 degree of freedom, so you only have one translation move to xs. Okay, any question? This is pretty simple because this is 1 degree of freedom. So let's move to the next 2 degree of freedom example. So this is a little bit complicated as compared to the first one, for example. Okay, in this case, we have 2 mass. We have M1 and we have M2. Okay, and then we have a component. We have components spring, viscous damper, and we have to consider as well the friction. This is the friction between the mass and the floor. This is friction FV1, and for the MS2, we have friction FV2. Okay. And to solve the transfer function, so basically the output of this system is x2. So the output is x2, where we put our input is the force, which is in this direction, Ft, that is applied on F1. When we put force on M1, what will happen is that there will be a translational move to the right, and it will also move the M2. Okay, and to solve this kind of question for 2 degree of freedom, the steps is we have 8 steps here. Okay, the first one, we only have to consider the forces on M1, forces on M1 due to only motion of M1. Okay, we have M1 here. We consider mass M1 and motion of M1. Okay, so we have to consider all across the M1. So we have K1, we have FV1, we have K2, and we have FV1. Okay, and again, next, number 2 is we find the forces on M1 due to motion of M2. So when we put force on M1, it will generate movement in x1 direction and x1 direction. And M1 is connected to M2 by the spring and the viscous damper. So there will be a counter force from M2 that is applied to M1. So that's why we find the forces on M1 due only to motion of M2. And finally, we combine all forces in step 1 and in step 2. Next one is we consider only the mass 2. We consider mass 2. Again, we consider mass 2 only to motion of M1. Next step is forces on M2 due only to motion of M1, and then we combine our forces in step 4 and 5. And finally, we can write the equation of motion by taking the step 3 and step 6, and finally we can solve the problem x2 over fs. All right, so let's do this step by step. All right, okay, the first one is we consider M1. We consider M1 only. We just ignore the first others. We only consider M1, where on M1 we have force applied on M1. So this is the force applied on M1. And then others is the counter movement due to force of M1, where we have the spring, is K1 in opposite direction. Because when you push M1, what we have is you have a spring connected to the wall, so there will be a counter reaction from the spring. So that's why you have uh, opposite direction of movement of a spring. So you have K1 X1S here due to spring K1. And then you have the viscous damper you have the viscous damper that is connected to M1 FV3. So you have again it will be in the opposite direction of F. So you have FV3S X1, and then you have spring K2. So you have K2 X1. Again, we have to consider the mass itself. So we have M. So the movement due to the force will be opposed by the weight of the M1. So you have in opposite direction of the force M1S2X1S. And finally, don't forget to consider the friction between the M1 and the floor. So we have in opposite direction of F, we have FV1S X1. Okay? All right. So now we consider the M1 due to the motion of M2. So we ignore this one. M2 again, we ignore this one. So we have the motion of M2, right? We have motion of M2, which actually due to applied forces of M1 of F on M1, it will move M2 in it will move it will move M2 in X2 direction. It will move M2 in X2 direction, which actually the movement due to motion of M2 is in direction of F. We have K2 X2 and we have FV3 S X2. So we combine 1 and 2, so we put in together, we will have the first equation here. So basically, this is the equation. So we have here is sum of impedance. Sum of impedance with motion of x1 minus sum of impedance with the motion of m2 of x2 equals to forces applied on m1. Okay, so you can verify with this equation. Okay, so this is actually sum of impedance. This is sum of impedance due to the motion of m1, which basically you have the spring, all the frictions, and you have the viscous damper, and you have mass m1, and then minus sum of impedance due to the motion of M2, which is you have this one, FV3S plus K2 of X2 equals to Fs. Similarly, you can find the next equation. Okay, the next equation is we ignore M1. Right? We ignore M1. So what we have is we have M2. M2 is connected to the viscous damper, spring K2 and spring K3. So we have K2 plus K3 X2. And then we have FV2 plus FV3 of SX2. This is the friction and the viscous damper. And then we have the movement of M2. So M2 S2 X2. And then we consider the movement of M2 due to the motion of M1, which is actually M1 is connected to the FV3 and spring. FV3 and spring. So we have these two equation, FV3 as X1 and K2 X1S. So we put in together into this equation. All right. So in this case, there is no sum applied forces because applied forces is only on M1, not on M2. Okay. So we'll have two equations here. And then we can find X2S over Fs. Okay. So please, so this is a summary of the example that we have done just now. So this is a sum of impedances connected to the motion at X1 minus sum of impedances between X1 and X2 equals to the sum of applied forces at X1. Okay, and for the second equation, we have a sum of impedances between X1 and X2. So this is we want to put it in this form because it is easier to see X1, X1, X2, X2. Otherwise, we can use X2 minus X1. So either one that you have you are comfortable with. So I think we stop here for today. What I want to do next is remember this one. This one. So this is your quiz 3.2. Yeah, this is the quiz 3.2. Find the transfer function x2 of over fs using Mason gain formula. Yeah, using Mason gain formula, find the transfer function x2 over fs. So later on, I will put in the Google form for you to submit the quiz. So the submission is must be made on Thursday before the lecture. Okay. Any question?